Hello, welcome to Aerospace Testing International's Roundtable, Next Generation NDT, working with aerospace composites. I'm Ben Sampson, editor of Aerospace Testing magazine, and I will be your host for this hour-long webinar. Today's roundtable will delve once again into the world of non-destructive testing, this time focusing on working with composites. We're going to be discussing best practice and new technologies in this area with some of the industry's leading experts in NDT, whom I'm sure many of you will know or at least be familiar with. On our panel today is Roger Englebart, whose 47-year career in NDT includes time in Boeing Research and Technology at St. Louis. He is also chair of the Aerospace Committee of the ASNT and its past president. We also have with us Robert Smith, who is Professor of NDT and High Value Manufacturing at the University of Bristol in the UK. Robert is chair of the British Institute of NDT's Technical Committee and also a past president of that organisation. Last but not least, we have representing the NDTMA, Dave Seto from UTEX Scientific Instruments, which is based in Canada. During his career with UTEX, Dave has designed novel ultrasonic probes, engineered automated scanning solutions, and has also developed customized software for automating inspections. So, Dave, thanks for coming. Can we just start with you? Perhaps you could just give everyone a little bit more background about what you do at UTEX and what UTEX does, just briefly.
Sure, thank you, and thanks for having us. UTEX is primarily a software developer and a producer of ultrasonic instruments and clever little widgets that we use for building automated inspection systems. I was dragged into UTEX backwards through the hedge. I asked, my training is actually in chemical process engineering, and I was working in the plywood industry, which is one of our earliest composites, looking for a way to do real-time monitoring of plywood adhesive curing. So I approached UTEX, and the next thing I know, I'm working for them. So that's how I got started, and yeah, I've been here for I think it's 20 years now. So yeah, it's been like you said, get smarter every day. Every day is a day.
You spend a lot of time working with aerospace clients, Dave. Is that?
Yeah, our clients are sort of divided up into two groups, mostly in power generation, and which is where we got our start, actually, and in aerospace, both in composites and in things like primary metals, and we have a few clients scattered into other areas where NDT is important, like exotic alloys and things like that.
Right. Okay. Thanks for that, Dave. Roger, I kind of skimmed over your 47-year career. It's maybe you could just give us, for those that don't know you or heard of you, that you could give us a bit more detail about that, please.
Sure, and thank you for having us, Ben. 42 of those years were spent inside of Boeing. So I've spent a lot of time focusing on the aerospace industry. A lot of that has been on implementation of NDT as a manufacturing support tool. A lot of it too was applied research and development, looking towards implementation of new methods, better techniques for manufacturing support. Some of that work was also in service, but largely manufacturing, and a lot of concentration on composites. I'm a metallurgical engineer by training, so it makes perfect sense that I would focus on composites instead of metals.
Right. Yeah. Okay. Good stuff. Thanks for that. Thanks for that, Robert. Roger, sorry, Robert. This is going to mess me up. Although Roger and Robert. Robert, thanks for joining us today. Can you just tell us a little bit more about what you do in Bristol? Bristol's a bit closer to me than Roger and Dave are, but can you just tell us what you do and a bit of background on your research, maybe?
Yes, certainly. And thanks again for having us today. So my research in Bristol started in 2013, and that is focused on ultrasonic 3D characterization of composites. That was a fellowship, which brought me from industry into academia. So before that, I spent 20 years in the UK civil service in research, mostly in the Ministry of Defects, and 10 years in industry in a research and technology organization. So I covered numerous sectors, materials, and NDT methods, but I guess I've specialised in aerospace and composites and ultrasonics. But even at the University of Bristol in the last 7 years, we've had programs on eddy currents for composites and X-ray CT for composites as well.
Great. Okay. Well, I look forward to hearing more about that during our discussion. So thanks for that. I'd also just like to take this opportunity to thank our sponsors. There is literature in the handouts tab on the right of your screen to download if you like. Our sponsors for this roundtable today are Zeiss, Magnaflux, North Star Imaging, VJ Technologies, and Element Materials Technology. So yeah, don't forget to check out the handouts. I'd also just like to add just a very short disclaimer that the views expressed by the panel during the roundtable today are entirely their own and not representative of any organisations or companies associated with the roundtable today. So just another couple of bits of housework for people that haven't done one of these with Aerospace Testing International before. There is a poll that we just like you to complete. It's not compulsory, but if you can find your time to do it, it should just start now. We'd just like to describe how you use it yourself as a user of NDT. That will help us give an idea about where to pitch the discussion, maybe. Secondly, the format of the roundtable, we're going to kind of talk amongst ourselves for 20 to 30 minutes. During that time, I'd encourage everybody to ask questions to the panel, either individually or as a group. They won't be displayed instantly, but during the second half of the roundtable, I will publish those questions as we ask them to the panel. So with all that done, we can kick things off. So Roger has very kindly volunteered to answer the first question. I hope it's not too straightforward for you, Roger. But I'd just like to ask about defects. What defects are we typically looking for in composites in aerospace? Which do we most commonly encounter? Which are the hardest to identify? It's kind of quite basic stuff, I guess, for you after 47 years.
Sure. No pressure with that 47 years.
I'm holding it over you.
Well, if you're thinking about solid laminate composites, the most common defects, of course, we're looking for porosity, delaminations, voids of any kind, possibly disbonds. If there's honeycomb involved, then they're added into that as core defects, skin to core disbonds, crush core, node bond separation, those types of flaws. I think probably the hardest in that group to identify is what we typically call a kissing unbond or a kissing disbond, a situation where the two surfaces are not joined so that there's any strength there, but they're actually touching well enough to pass ultrasound. Very difficult to find. And there may be some discussion later on about technology developments that improve that. I think probably the defect that we're going to spend the most time on is porosity. Porosity is common. It drives the allowables for the material. It drives the knockdown considerations. And we spend a lot of time not only finding that it's there, but also characterizing it. It's usually not enough to say, yes, you do or do not have porosity, but there's usually a allowance of a maximum percentage of porosity over a certain area of the composite structure. And very often the engineering organizations want to know, well, how much do you really have? How far does it extend? What percent is it? And that leads to, in preparation for that type of thing in manufacturing, it leads to a round of developing a whole host of porosity standards of varying percentages and varying ply thicknesses, which becomes quite costly. So a lot of focus on that anomaly in particular.
Okay, thanks. Roger, I'd just like to ask you as a starter, Robert, even though your names are on the screen, it's going to happen all three. Sorry, my apologies. Robert, I'd just like to ask you, there's always developments in materials and composite materials as well happening. It's a constantly evolving thing. What's happening in materials at the moment which might impact the way that NDT is done with composite parts?
Well, okay. In terms of materials as opposed to manufacturing processes, then I guess the move to 3D woven composites, even 2D woven composites provide additional problems. When we go to 3D, then it is quite difficult to distinguish the internal structure that should be there from what is a deviation from design. So I think that's a fairly challenging issue for NDT in the future.
Okay. In terms of manufacturing, you were going to say, is that a different? What kind of problems is that causing, or challenges, should I say?
Well, I guess there's a move to out of autoclave manufacturing. So resin infusion kind of processes where you haven't necessarily got good consolidated material at all stages in the process, and so actually the aim of all manufacturers generally, it seems, of composites is to not have to do NDT, and so the hope, as far as I can tell, is that we potentially move the NDT earlier in the process. So pre-process and in-process NDT and monitoring there are research projects going on that. I'm not sure how much has actually been implemented yet. So you're talking about trying to find precursors to defects. You're looking for changes in say a dry fiber preform before it gets cured that might ultimately result in a defect if it were cured in that state. The great thing about doing that is you have the potential for rectification before you do the final production cure.
Okay, right, that's interesting.
Ben,
sorry,
if I could briefly, I'm sorry, if I could briefly follow up on what Robert said, in line with the material systems that he mentioned, there's a drive towards looking at unitized composite structures, larger pieces, single part manufacturing as opposed to a number of different parts and assemblies. And the business case for this reduces assembly costs, it reduces weight of fasteners, it reduces the inventory for hardware. But because of the size and the complexity, and now it's a single piece, it changes the NDT operation because you're looking at larger systems, more complex operational cells, and that's just speaking to Dave's expertise. But you're also thinking more seriously about defects and defect locations, because with the size and the investment of a structure like that, there's less interest in dealing with repairs and rejections and more interest in trying to save the structure. So it changes how the cell operates.
Dave, you're nodding your head in agreement. Do you want to talk around that, or?
Yeah, absolutely. I mentioned one of our client areas is in doing systems for power generation, and when you've got a forging that's it's a powder metallurgy process for a lot of them now, and it's worth $500,000 by the time we get to it, and that's one of the small ones. That's just when you've done the machining for the ultrasonic shape, and the same thing applies there. Exactly what Robert was saying. They want to know before they even start that the powder that they're going to use is absolutely perfect and has no inclusions that will show up later in an ultrasonic scan. So the material science, the materials evaluation is so important at that stage. And then by the time we get a hold of it and put a 9-ton forging into a tank of water, boy, it better be perfect. Like we're really just there to verify that all of the preceding non-destructive testing and materials analysis has been done appropriately and correctly. And then as Roger was saying, when the parts get that big and that expensive, nobody wants to see it scrapped or melted back down again. So we'll talk to this later, but one of the things we do is try to figure out, okay, is that defect in an area within a 3D volume that you're going to machine away anyway, in which case it's fine, like record it, but you don't reject the part, you try to save the part. Yeah, and we're seeing the same thing with our clients in large aerospace structures as well. They by the time we get a hold of it, it's worth millions, and nobody wants to see that part, somehow not make it into use.
That idea that you're identifying potential problems as early on, that extend to working with, collaborating with the structures and design disciplines within an organization. I mean, and how can people doing inspection and analysis, how do you work with those people closer? Can anyone talk around that maybe? Is that?
I can take that one to start with, Ben. I
Sure.
think that very often in organizations, the operations like manufacturing, design, analysis, quality assurance, and NDT are somewhat siloed, and they have their roles in production of the product. But there needs to be a really good collaboration, interdisciplinary team approach to any of those projects. And NDT absolutely has to have a seat at the table from the very beginning. When the project, new aircraft, new product, whatever, begins with a series of concepts and trade studies on what materials should we use. Am I going to do solid laminates? Am I going to do unitized structure? Am I going to do honeycomb? And NDT can immediately begin weighing in on what the costs and the advantages and drawbacks may be to an approach, and begin to help define that, and also know as they're going along more about what the structures community is thinking, how they're thinking, and what's coming along, rather than finding it out much later in the process. It really is important to the overall cost of the program down the road.
And is that something that you think manufacturers are embracing that approach, or is that message taking a while to get out there?
I think it's a slow process. Some projects handle that better than others.
Mm-hmm.
Within any given organization, it's probably done better in small R&D projects, but it's something that absolutely has to happen. As Robert said, the goal is not to have to do NDT, and there's a cost associated with it. There's a cycle time associated with it, and the more things that NDT can account for up front, configuration, geometry, access to critical areas, realistic criteria, the more it will help positively impact the business case and the cost down the way.
Mm-hmm. So just to really stress this point, I guess, Robert, I mean, how early on in the development process do we start would you like people to start looking for defects from the very beginning?
Yeah, well, I think that NDT has a lot to offer at the design stage. Mm-hmm. So we have a big program in the UK now looking at whether by building in more NDT at the design, in the design cycle, whether you could actually increase the confidence in a virtual testing rather than actual experimental testing. The aim would be to replace as much as possible of the actual mechanical testing with models and simulations. One of the problems is that it's difficult to validate those models, partly because the experimental tests have such a large distribution of results. And that is partly because the composites themselves have quite a high amount of variability. So if you test 100 coupons, each of those coupons is going to be slightly different. So there's potential, and manufacturers are beginning to see this in terms of supporting research programs, in terms of using NDT on each of those coupons for each of those tests, to prove what is actually there. So what are you actually testing? You're generally not testing exactly what you designed. You're testing a variation on that. You're testing what you manufactured. So potentially you can improve the validation of the virtual testing, and take out swathes of the mechanical testing phases in what's called the design test pyramid for composites. And so that's what that's one of the goals, and that is very much about getting involved with NDT at the design stage, and even instrumenting those tests the actual mechanical tests that go on with thermal stress analysis and digital image correlation, that kind of thing, to know what's going on during the test. So I think we're going to have people wanting us to be able to support the designers. It's not just going to be about at manufacturing stage or in service, it's at the design stage as well.
Dave, I think it was you mentioned inline inspection in manufacturing. Is that part of this picture as well?
Oh, absolutely. You know, in the case where you have to inspect the part because the manufacturing process itself might induce defects, you're stuck with NDT. Like there's no escaping it. So one example is composite clips. We work with a manufacturer who makes the thermoplastic laminate, and that gets inspected. So, you know, back up the process to make sure that the material you're using doesn't have any, you know, porosity or delaminations in it. But then once you start cutting it and bending it and folding it into something like a, you know, fuselage clip or a wing skin clip, you've bent and drilled holes in it. So now you got to do NDT again. So, you know, hopefully ultimately they'll figure out how to do that manufacturing with water jet cutting or some other mechanism, and then statistically prove that mechanism does not induce defects. Another example that we did speaks directly to what Robert was just saying. There's a process for peening compressor blades, titanium compressor blades for jet engines. And you know, the old days it used to be shot peening, but now you can do laser peening. And the laser peening process early on was thought to be better. I think it is. It does more of a through hardening than you might get with a surface peen. And so that has benefit for a titanium blade. But the worry at the time that the manufacturer was developing this was, are we hitting it so hard with the laser that we're actually, the shock wave might be inducing cracks in, you know, things like the galleys and the cooling channels and stuff like that inside the structure of the compressor blade. So we were involved in a process. They were going to do this with lean manufacturing. You know, a robot picks a blade up out of a carousel and then bangs away at it with a laser to peen it, and then the mirror image of that robot picks the blade up and runs it through an ultrasonic scan to make sure that the peening process has not induced any defects. And at the time, they thought that they would do that as a manufacturing process, that would be the process. The blade gets peened, and then the blade gets inspected. But along the way, they very cleverly figured out that, hey, we just need to prove that the process is statistically reliable, because the laser is very, very reliable, right? Even more reliable than shot peening. So they only ever built 2 systems, and that was basically to prove that when we peen them in these parameters, these blades are not going to have defects. So the NDT was part of the design process for the product and for the you know, the manufacturing process, but it's not, the NDT is not used. It's only used to qualify new blades or new parameters. It's not used in manufacturing.
Great, thanks, Dave. I mean, Roger, the type of things that Dave's talking about there, the kind of problems, are they the kind of things that you would be encountering at Boeing? And, you know, what the kind of solutions would you be forced to come up with?
Well, we're looking at all different types of manufacturing applications, and I know that we may be talking about this a little later, picking the right method for the right application. In terms of aerospace composites, a lot of what we're doing is ultrasonic based. That is sort of the baseline and favored method for composites inspection. But we'll also look at more advanced techniques if the process calls for it.
Great. Okay, sure. Robert, I'd just like to ask you, things like advanced imaging and analysis techniques. I mean, a lot of the time, you know, you're trying to look at the internal structure of a composite. I mean, what kind of role do those kind of advanced imaging and analysis techniques have? What are you looking at? What's the application of them at the moment?
Yeah, certainly for what I was talking about at the design stage, what you're talking about is 3D characterization of the internal structure. It's not quite the micro scale, so it's not fibers. It's what we would call meso scale. So it's fiber toes, plies. What are they doing in the structure? Are they doing what they were designed to do? So X-ray CT has really come into its own probably in the last 10 years, partly through developments in X-ray CT, the ability to go to smaller resolutions, but then also to be able to do that on larger structures, so realistic structures. You no longer have to make a really tiny sample in order to get high resolution. So and X-ray radiography was really something that was beginning to be replaced in a lot of applications because of some of the safety issues, and because it was quite hard to find most defects in composites with it. So X-ray CT has made a massive change to the scene. But what we're also spending a lot of time on is trying to do exactly that, but with ultrasonics. And the main driver for that is to be able to do it on really large structures. So can you scan a wing, or can you actually apply these analysis techniques to the scans you're already doing on a wing? Because manufacturers really don't want to have to do a second scan. So can you take that data and maybe change slightly how you acquire the data, or what frequency you use or whatever, but can you analyze that data and get the information about exactly what's going on in the structure, that all the ply drops are in the right places, there's no waviness. If there is waviness, how much is it? How big an area is it? What's the biggest angle of the waviness of the fibers and things like that. So it's all about increasing confidence that the as manufactured component conforms to the design.
Okay, great. And you mentioned X-ray CT. There's still, I guess, relatively new technology. I mean, we've done several webinars on that. It's funny enough. So, I mean, but including that technology, Dave. I mean, I'd just like to ask you. I mean, are there any? When we've talked about ultrasonics quite a lot, are there any other NDT technologies that are really impacting the way composites are inspected, or could do in the future? Anything up and coming?
Yeah, we're working on a couple of things for some clients in the wind power world. Microwave, it has been sort of getting ready to leap out of the lab and sort of, cross the chasm into commercial deployment. So we're working with some clients who are already in small scale deployment of microwave imaging systems. So one of the things that's driven that actually is electronics. It used to be that if you wanted a vector network analyzer, to do a spectrum sweep across the gigahertz range, that was well, when I started my career, it was $100,000 instrument, and you could get a cheap one for $50,000. So that's not outrageous when you think about what modern phased array instruments cost. But back in the day, that was a huge amount of money. But now you can get a really competent vector network analyzer. That's the size of a sandwich for about $10,000 or $15,000. So all of a sudden now it's portable, it's digital. You can what the part that we're doing is the software analysis, so it's quantitative now. Whereas before it was a little bit subjective. It was very much like how we used to do thermal imaging and even ultrasonic imaging. We'd sort of look a human would look for blobs in the image and go, that blob's supposed to be there because it's a fastener, and that blob's not supposed to be there. So what do we do about it? And so yeah, microwaves I think going to be coming on strong for especially for dielectric materials like fiberglass, and then we're working with some clients as well on terahertz imaging. So again, that's been driven by the well, actually probably by the security industry first, right? The airport scanner is a terahertz imaging thing when you stand in that booth. So it's quite good at near surface, high resolution imaging of near surfaces. We have one client who's able to image layers in a ketchup bottle. I don't know if you know this, but your standard Heinz ketchup bottle has as many as 7 layers of plastic in it. And terahertz imaging is capable of the resolution where you can pick out those individual layers, and you can look for lack of adhesive between the important layers. So in composite solid laminates, or the bond between the laminate and the foam, or the laminate and the honeycomb, that's huge. So we have a couple of clients in the aerospace industry working on deploying that technology on a large scale. Like when I say large, I mean like spacecraft large, or air large commercial aircraft large. So your little airport scanning booth, that imaging system is dinky compared to what people are getting ready to deploy.
And that technology is scalable in that way, is it? It can be.
Yeah, because it's just a probe, right? So it's like phased array, right? It was magic 30 years ago that you could steer a beam, and now everybody does it. You can do it with an iPhone, apparently, if you have the right app and the probe. So yeah, it's just a bigger array, and it's generating terahertz waves instead of so we're sort of we're in that band between the infrared and the microwave. So at those wavelengths, certain kinds of defects, like delaminations in a skin, it's really sensitive to those. So it's not going to replace ultrasound necessarily. If you have a big thick composite core structure, you might still use through transmission ultrasound to inspect that. But at the same time, the robot or gantry or whatever can be carrying a terahertz imaging head, and you can look at the near surface and look for delamination in those top couple of layers.
Okay, great. And we're past the halfway mark now. So I just encourage people to keep asking those questions. I just wanted to ask one more question, slightly moving away from what we have been talking about, more about the profession, really. I mean, we have representatives from 3 different associations here to do with NDT, which is fantastic. I mean, the training and development of new technicians and engineers in the field of NDT. Do you feel that's you've got a good pipeline of people coming into it at the moment? I mean, how do you best go about doing that? Anyone want to take that, Roger or Dave? Or?
Well, I guess. Go on, Roger.
Go ahead.
Okay. Right. Well, I guess in the UK we've identified an issue with composites. We have a lot of technicians moving from metallic structures to composite structures, and it is totally different because the product that they're inspecting is different. And so we actually put in place a program to develop training courses and qualifications to move people from a more metallic background into composites. But there's a lot of work to do. We've started with maritime composites. That's partly because in aerospace, the individual companies have taken on this requirement themselves, whereas in some of the other sectors, it's slower and harder to actually make it happen. So I think that's a big issue. But I also think that we're with Industry 4.0, the 4th industrial revolution, which we haven't talked about much yet, but the way things are going with more automated analysis, continuous monitoring, machine learning techniques, artificial intelligence, then potentially the workforce is going to have to shift in terms of its skill set, and we're going to need more people who understand about validating automated systems as opposed to people who can actually make the decisions themselves. And then you end up with all sorts of issues because the people validating those systems actually also need to know how to make the decisions themselves. So you end up with losing that skill set. So we've got a lot of things to think about in the next 10 years or so as the whole environment for manufacturing changes with Industry 4.0.
Do you guys agree with that read of the situation, Roger? Is that?
I do. I think those are definite, very valid future considerations. In terms of whether or not we have a good pipeline of people coming in, good experienced NDT practitioners that have had certifications are always in demand. Any company and any product line wants somebody to come in at a level at which they can immediately begin inspecting and making accept reject decisions, because that's where the need is. But it's very different. Moving between very different industries and applications is difficult, as Robert pointed out. Somebody coming in who's very experienced and very capable in the oil and gas industry moves into aerospace, and it's just a whole new set of materials, types of criteria, approaches, and in some regards, it's like starting over. So to bring your folks along, you really need good on-the-job training internally and good specific training as needed for the product line and your requirements.
Yeah.
Dave, any comment on that, or just to confirm?
Just corroborating it. Yeah, absolutely. We are asked mostly to help people with automating processes that they cannot get technicians to fill that role, or in some cases where a human technician is not really appropriate. Hundreds and hundreds of small parts a day is not something you want to spend your life doing. You'll have carpal tunnel syndrome by the end of the week. But the value of the human is not in dragging the probe around. The value of the human is, as Robert said, how do you know that that's a good part versus a bad part? So obviously there are standards that you may be able to program into a robot, but how do you know that the robot's doing a good job, right? How do you know that the robot is correctly holding the probe? Is it aligned to the surface? Are you even illuminating the material of interest with enough energy to actually detect a defect or not? So we're finding that the pipeline of sort of old school NDT practitioners as a profession seems to be I won't say it's not there. It's just that I don't know, perhaps the people's traditional interpretation of what NDT is. You're going to put on your work boots and get in a dirty hole and drag a probe around on a pipe is not what NDT is anymore. But when I talk to students in high schools, that's what they think of it as. So when I say no, you're actually going to learn how to do material science and then program a robot, and you're going to have a giant 4-screen monitor system where you've got to keep track of a $5 million robot inspecting a $20 million part. Are you up for that? And so that, I think that's where we could probably do the most promotion, through ASNT and BINDT, is talking up the need for a team approach, right? We need material scientists, we need computer programmers, we need robotics and automation experts, and we need people who have that traditional NDT background to help interpret it all. Because the stuff that we do, we're always talking about how stupid the machines are. The machines just do what they're told. They need a clever human to tell them how to do it properly, and then to monitor them and make sure that the process is proceeding as planned. Right.
So we need clever humans. Okay. Yeah, I agree.
Absolutely. Most of the people where we're involved, they tell us that they're hiring, not getting rid of NDT people. They're hiring a higher caliber of person, and they're paying more because they need the expert analysis. We can automate it to a certain point and say, okay, out of these 7,000 parts, you just want to look at these 10 or 20 that have some sort of subjective interpretation is required. Are you going to save these parts or throw them away? You need a human to do that, and they need to understand as well, basically what we call supervisory control, right? The robot's just going to keep picking up the part and hanging it in front of the probe, and picking up another part and hanging it in front of the probe. So a human who knows what's supposed to be happening, both with regard to the physics, and the standards and specifications that dictate whether the part is acceptable or not, they have to be there. They absolutely have to be there. So they just need another skill set. That automation and computer programming are now part of NDT.
I think that's something that a lot of the people, the participants today, would like to hear. I've closed the poll now. I'd just like to read out the results. So of the people tuned in today, 37% are end users, classify themselves as end users. 38% classify themselves as suppliers, and 25% classify themselves as researchers. So I'm not sure if that's 100%. I guess it must be. But yeah, it's a good mix of people there. So that's great. Thanks for doing that. We'll just move to the Q&A section. Thank you, everybody, for submitting those. We've got several to get through here. I will start at the top with Adrian Loggins' question. Adrian would like to know how important is taking into consideration manufacturing defects, such as porosity, when designing a composite structure. Do designers have to come up with personalized FEA models that capture fabrication-related anomalies for structural integrity assessment? Seems quite complex, that question. Maybe take the first part if anybody fancies that.
I'll take a run at that, Ben. As we talked earlier, the presence of porosity really drives the material allowables. And when people are qualifying a material or developing allowable properties, they're looking at the content of that porosity and its effect on those, and how much porosity can I have in this area before I have a loss of property or a knockdown, and how does that affect my criteria? Engineering looks at that very carefully. They absolutely have to have an analysis methodology to give them that, and they do. How specialized does that become? Probably as the parts get larger, more complex. We talked earlier about the impact of that on NDT in terms of the expense of the operation, accessibility, and the ability to inspect it fully. You really need to take a hard look at the analysis results for that entire structure and be aware of areas that are particularly critical and maybe areas that are not so critical, so you can tailor the criteria in order to get an acceptable result.
So I think one of the things on the porosity question is that at the moment the methods for measuring porosity are relatively simple, crude, and they use it's often a kind of a through thickness average porosity measurement that is obtained usually from ultrasonics. One of the things that is seen as a benefit in the future as structures get more complex and we try and push composite design to their optimum is to do 3D characterization of porosity, so that we're no longer using this through thickness average, and then the kinds of decisions that Roger's talking about could be based on an assessment not just of the average void volume content, but the actual location of where that porosity is. I guess there's another part to this question, which is all about personalized finite element models.
Yeah,
I mean, certainly there's a lot of work at the design stage on trying to determine the effects, as Roger said, of porosity and other kinds of defects that can occur at manufacture, and I would say that the aim is to have a full finite element model of a structure. It's probably not happening in civil aerospace at the moment, but is happening in military, in defense aerospace, and being able to exercise those models to determine the effect of defects is absolutely crucial to the design process.
Okay, thanks, Robert. Let's move on to this question here from Ken Hardy, who's asking what are the expected effects of hygroscopic moisture and solar radiation on the breakdown of composite materials, and what NDT processes show promising is detection. So I guess he's talking about inspection and the way that sunlight and water affect materials. Am I right in thinking that? Yeah. Anyone want to comment on that or have a stab at it? It's not something I've ever encountered before, I must say.
I'm not quite sure where that's coming from. So different sectors would potentially have different requirements here. I'm wondering whether that's a space requirement or something in terms of solar radiation. But
maybe can you clarify for us further down? We've got quite a few to get through. So Mark Dowell's question here, I'm going to, he's talking about training and qualifications and technique validation, making use of specimens containing example floors, which is specifically fabricated to simulate specific defect types. Can anyone see that question? Is that?
Yeah, I had a look at that in advance.
Producing consistent defect specimens for training or examination purposes for composites. Is this even important?
Yeah, well, it's very important, and I've been involved in a program some time ago, actually, about 20 years ago, trying to produce consistent defects in specimens, a standard specimen, reference specimen. I'm sure Roger's got many tales of trying to produce specimens like this for just about every component, but my understanding is what tends to happen is that the manufacturer will produce a component which is very similar to the one they're trying to produce that has defects in it. And I've certainly seen, whole wing spars that get scanned before and after the inspection. The system is passed over this standard wing spar with defects all over it to just check that it's that the system is going to find the defects. Now, whether that kind of idea can also be used for personnel training, does anybody have any experience of what happens in composites training programs?
I think it's very much like you described. It's also a situation where as the manufacturing goes on and there are scraps or rejects, sometimes those parts are able to be carried away and kept as reference standards for a particular anomaly that it would be very difficult to reproduce. I think the biggest challenge in creating standards is when you're talking about porosity, because you have to try to produce a certain percent porosity and a certain thickness of laminate intentionally. If you don't want it there, you'll have no trouble producing it. But trying to do it in a disciplined way is very time consuming. It's very expensive. And to do that, you have to have an entire range of porosities. You end up actually developing a curve, which is part of your machine qualification in the NDT cell of percent porosity versus attenuation that requires lots of samples and pretty challenging. But those samples can also work for training technicians as well.
I guess one of the big issues is that the same sort of artificial defect is not appropriate for all methods. So even a straight delamination, you wouldn't necessarily produce that artificially in the same way for a thermography method as you would for an ultrasonics method or an X-ray CT method.
Okay, right. I'm gonna deliberately pick the shorter questions here, I think, because we're running short on time. We've got about 10 minutes left. There's one here from Stephen Bartlow who asks succinctly, well, what is the future for IR and pulse thermography in relation to composites? So Dave, that sounds like you might know something about that.
Yeah, but I probably can't talk about it too much, other than to say that, for certain kinds of components, aerospace components, we have clients who are using pulsed thermography, and they're attempting to qualify that as an alternative to ultrasonics. In some ways, it's complementary. So the debate right now among suppliers and users of those composites is the pulsed IR enough? and it's lovely because it's fast and it's dry, right? A lot of ultrasonic methods in aerospace involve water splashing everywhere. So an IR method is nice because it's quicker and you don't wet the part. So that's lovely. But I think, you know, maybe Roger and Robert will have more insight about whether or not the jury is in on can it be used, you know, for the parts we're thinking of have laminate and foam core with metal inserts, and so what they're, you know, they're pulsing the whole part in one big cell and then doing the time series imaging. So we're involved in that just sort of as an R&D thing, helping them with the automation of it and the analysis of it. But it's not deployed yet. It's not approved, at least not with this particular customer of ours.
Any comment on that, Roger or Roy?
I think that, you know, Dave's absolutely right. It's fast. It's non-contact. There's no moisture involved. And so the speed and the convenience are very attractive for manufacturing operations. I think one of the challenges, and this speaks to the question that follows Stephen's, is that if you're trying to qualify that as an alternative method, let's say for ultrasonics, the manufacturing and the structures community are used to seeing what ultrasonics produce, especially in terms of porosity. They're used to seeing that porosity is judged in terms of how much sound attenuation there is through the laminate. Now you have to prove that IR is going to give you equivalent or better data a different way. Instead of looking at attenuation, you're looking at thermal diffusivity through the laminate. And you have to show side by side with ultrasonics that you can produce that in order to give them that comfort level as an alternative method. You've also got some thickness limitations in terms of how effective that is through the laminate, because there's lateral heat dissipation through you know, the carbon-based composites, and it limits how deep you can go to make that effective. So there's definitely some work to be done to bring that along, but it is very attractive. Okay,
I'd like to ask this one next for Thomas Kunsel. I apologise, Thomas, if I've mispronounced your surname. It's about specific parts of an aircraft. He wants to know if digital radiography is a reliable solution compared to ultrasonic inspection for highly integrated composite structures with skin to spar joints, including radius fillers. Does anybody want to take that, or we can skip over?
I think the thing would be to ask, what are your criteria? Mm-hmm. And what are you looking for? If you're looking for maybe something, if you have a situation with fillers where there's a potential for a void or an incomplete filler, then yes, this might be exactly the thing to do, particularly for the very complex areas. Mm-hmm. But for porosity, delaminations, the types of things you're normally looking for, I would say no. Robert, what do you think?
Yeah, it's all about getting good contrast between defective and good material, and that is very subjective. It depends on the orientation of your defects. With radiography, you're not talking about computed tomography, I guess. So you've got a particular direction that you're radiographing it in. A lot of the defects are sensitive to the angle of the X-rays. So you really have to spend quite a bit of time validating for all the scenarios you're looking for.
Great, thanks, guys. Sorry, I do apologise. I've been forgetting to publish the questions again. I've one job as host, but I've just caught up with myself. So if people are expecting their questions to appear, they will do now. Robert, I feel like we should answer this one. This is a question for you from Henrik Rees. He wants to know about ND parts of engineering degrees, mechanical and civil engineering degrees. Is an NDT course required for an engineering degree, such as mechanical, civil, etc.? And if not, can undergraduate students take NDT courses as electives?
Yeah, I think it's an important part of any engineering degree. I wouldn't like to say that all engineering degrees include courses on NDT, but certainly a lot do in the UK. We obviously have certain universities that specialize in NDT more than others, but it's very important. Don't know whether that's also the case in the US.
Yeah. Nodding of heads. Yeah.
Yeah.
Okay.
In fact, that's ASNT has a relatively new engineering council that looks just, at those types of things. How can we better serve the engineering sector of the NDT profession as opposed to the technician or practitioner and the researcher? And it's very much about what institutions are offering, what types of courses can you get to a specialization in NDT engineering. We're very interested in that.
Okay, thanks, guys. This is quite an interesting one here from Kalian Forrester, who asks, is the development of new materials outstripping the development of NDT to inspect? Is that a bit contentious? I mean, are you always trailing behind the material scientists, the NDT guys, or is that not just the way you'd look at it?
I think that there's a lot of potential there. If you think about the end user community, those people their goal is to manufacture and sell a product. And a lot of times the feeling is, well, if we can't manufacture or build it, we can't inspect it. So the inspection part of this is not as important as the materials and manufacturing processes. And what happens in the developmental world is very often the materials and the manufacturing R&D efforts are funded over the NDT. So NDT lags behind in the resources to do the development.
Yeah, I guess somebody's got to have the idea of and do the initial research on a new material before they can define what the NDT requirement is. But there are certainly cases, particularly in things like 3D printing, where the applications are restricted until the NDT has caught up.
Yeah.
You're probably always going to have an initial lag, but then you also might have a requirement to catch up later.
More collaboration. Okay, great. I'd just like to ask this one from Jez Duggard, who says that the conversation so far has concentrated on manufacturing, but some of the bigger challenges, I guess, that Jez encounters are how to detect issues that have occurred while in service, aircraft in service. I mean, how much effort is expended by design organisations to look forward about how to inspect composites once they're in use in the field? Is that a big effort? Can anyone talk to that?
Yeah, that is a big effort. Whether it's a commercial or a military product, the manufacturer has a whole set of recommended inspection procedures and applications to go through that are a part of, if you will, the repair literature, the maintenance literature that goes with the product. And they have done those types of trials internally. And it's a continuing effort with delivered items. If there's a problem encountered in the field that's new, the manufacturer works it, comes up with a solution, and issues a recommendation to the field, the airlines, or the users in the field on how to handle that inspection. So it's very important.
Okay, great. Thanks, Roger. We've got time for 2 or 3 more questions. In particular, I'd like to ask this one from Vin Sharma, who calls back to something we were talking right back at the start. He's asking, what are the available methods for detecting kissing bonds?
Yeah.
No pressure.
Okay, well, maybe I should chip in on this. I mean, a kissing disbond, for those who don't know, is supposed to be a 0 volume but very low strength bond. So potentially the 2 surfaces are still in intimate contact, but can't transmit a load. So that does present quite a bit of a problem for many techniques, because things like thermography, you potentially can still transmit heat across, you can potentially still transmit ultrasound across that boundary. So as I said earlier about looking for the contrast between good and defective material, what you want is something that sees that kissing disbond as different to a good bond. So the kinds of things that are being looked at are methods that would put that bond line in tension and open it, because that is possible with a kissing dis bond and not with a good bond. So there's been a lot of work on nonlinear ultrasonic methods, for example, and shear wave and transverse and longitudinal wave methods, and there's actually quite a lot of promise. So I guess the bottom line is there is no real definite solution yet. This is still the holy grail of NDT inspection for a true kissing bond. There are lots of people who claim to be able to detect kissing dis bonds, but you have to ask the question: is it really a truly intimate contact? That's the challenge. So nonlinear techniques are looking for a difference in the stress strain curve for compression versus tension. And there's a lot of promise in nonlinear ultrasonic techniques.
Okay, thanks. So just the last question here. I think I'd like to ask this one from Matthew Robert. He says he's asking, after program failure, such as I think he's meant the Learjet AE5, or we can just take program failures. Do you see that the aerospace industry is showing less interest in using structural composite parts due to the complexity that's linked to manufacturing inspection? I guess his point is does this put people off? Does the complexity put people off using composite parts, or is the trend towards lightweighting so strong that people are just going to do it anyway?
It's hard to tell from Matt if he's talking about unitized structures or just using composites in general. Mm-hmm. But I think the strength and weight trade-offs are so good that we're going to continue down that road, and we're going to continue with the materials development and move towards, as Robert pointed out of autoclave processes, less expensive manufacturing. I think that this question points to what we talked about earlier with unitized structures, because you have complexity and a lot of investment by the time it reaches the inspection operation. You really have to think about your criteria, accessibility of the design by inspection methods, good manufacturing processes to make sure they're repeatable and you have as little in the way of discontinuities as possible.
Okay, thanks, Roger. Anyone else want to close off what we're talking about here, or is?
No, we're seeing.
I mean, I think it's been a fascinating discussion. It's a great area, and it always interests me that there's so many sort of niche technical challenges within this area that people are facing every day still, and problems that have to be solved. Even though we're so many, it's such an advanced area as well. It keeps throwing up challenges. So all that remains for me to say really is thank you everybody on the panel for I know that can get quite quick fire, the Q&A session. So that's great for you guys to do that. Thank you, and thanks to all the audience and the participants for asking your questions and answering the poll and indeed turning up. Thank you to the sponsors for making it happen. The roundtable will be available via links on our website, and you'll also get an email so you can watch it again if you want. There'll be another one next month, probably not on NDT, but keep your eyes peeled. Thanks and enjoy the rest of your day. Thank you, everybody.
Thank you, Ben.
Cheers.
Thanks.